Every Boolean expression and equation has dual interchange. So basically, the OR operation is interchanged with AND 0 is interchanged with 1. So if we consider our Boolean algebra here, and the identity property, we see that these properties are duals of each other by interchanging AND with OR and 0 with 1. And similarly, the associative laws are duals of each other, where the OR operations can be interchanged with AND. And the distributive laws are also duals of each other. So we can see that the OR and AND operations are interchanged between these two laws. Now De Morgan's laws state that not X or Y is equivalent to not X and not Y. So this is De Morgan's first law, which has a dual being not X and Y is equal to not X or not Y. So we can see the interchange between the OR and AND operations. And let's show that De Morgan's first law works using a truth table. So taking the simplest elements from the Boolean expression, we have X and Y first, being the inputs. So all the possible permutations of X and Y are 0, 0, 0, 1, 1, 0, and 1, 1. And then the next simplest elements are not X, not Y, and then X or Y goes in the next column. And then we have not X or Y, and finally not X and not Y. So the complement of X is 1, 1, 0, 0, and the complement of Y is 1, 0, 1, 0. And then for X or Y, 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, and 1 or 1 is 1. And then the complement of X or Y is 1, 0, 0, 0. And then not X and not Y, so 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0, 0 and 0 is 0. So as we can see, the last two columns of these Boolean expressions are the same, and therefore De Morgan's first law holds. So as an exercise, construct a truth table for De Morgan's second law and show that it's valid.